Assalamu alaikum everyone. I hope you all are doing well and taking good care of yourselves. This is your instructor Ali Faruqi and you're watching Science with Ali. This is the part 3 of chemical energetics and we will be starting this right away. So a quick recap of what we did in part 2. We discussed the particles have certain energy present in them at all times. We gave them energy of reactants and the title of energy of products. We also discussed how the energy of the reactants and the products will never be equal. It will always be this way, that the energy of reactants is more than the products, or the energy of products is more than the reactant. Moving forward, we discussed how to classify endothermic and exothermic reactions in the form of an energy profile diagram. We also discussed how a reaction cannot start independently before we even provide activation energy, which is the energy required to start a reaction. I gave you the example of the stove, in which you had to light up a match or a spark in order to start a fire in the stove. Now, because this was an exothermic reaction energy profile diagram, our enthalpy change, which was the enthalpy change, the delta H, which is represented over here in the form of a graph, it came a negative value. Because it was negative, we can indicate that this was a exothermic reaction. Moving on to endothermic reactions, we discussed how the energy of the reactants is always less than the energy of the products, meaning that in an endothermic reaction, we will also be providing them with activation energy, but also some energy will be provided to the reactants themselves so that they have enough energy to react to make the products. That is excluding the activation energy. Therefore, we concluded that the energy of the reactants is always less than the energy of the products. And after we calculated the enthalpy change, which was the energy of the products minus the reactants, a positive value was obtained, which indicated to us that the reaction was endothermic. All right. Now, in today's class, we are going to be talking about bond energies and see how we can use them to determine whether a reaction is endothermic or exothermic. Now, when we think of a bond in a molecule, what image comes to mind? I'm guessing something like this. This is a molecule right there, and this is a molecule right here, and they are joined together by this particular bond. So when I want to say I want to break this bond or even make this bond, I will have to look at what is bond energy. So bond energy is the amount of energy needed to break 1 mole of a particular covalent bond. So if I have an atom of hydrogen bonded to an atom of chlorine and said that the bond energy was positive 431 kilojoules per mole, that means that we will have to supply 431 kilojoules per moles of energy to break 1 mole of these compounds. Hence, it was a decomposition reaction, as we discussed in the previous video, that if an enthalpy change is positive, means that the reaction is endothermic. And one thing to remember is that this 1 mole is 6.02 exponent 23 particles, because this is Avogadro's constant. All right. So breaking bonds is actually an endothermic process, as it requires energy. So it is an endothermic process. On the other hand, bond formation is an exothermic process. So if I were to form 1 mole of HCl bonds using hydrogen and chlorine to form HCl, it would actually release 431 kilojoules of energy to the surrounding, and it will be a negative process because it is releasing that energy. So if we took this simple reaction like hydrogen plus Cl2 give us 2 HCl, and we were to think about it in terms of molecules, we will have something like this, right? As you can see, there are two atoms of hydrogen, so there are two atoms of hydrogen as well over here, Cl2, and there are two bonds of HCl, so there are two bonds of HCl represented over here in the form of a displayed formula. So if we were to think about this in terms of molecules, as we have drawn over here, then we can see that for the reaction to work, we will have to break this hydrogen-hydrogen bond and this chlorine-chlorine bond, which would require energy to do so and be endothermic processes, and they would form two of these HCl bonds, which will release energy to the surroundings and be exothermic processes. Now we know that breaking bonds is endothermic and forming bonds is exothermic. To determine if the overall reaction is exothermic or endothermic, we would have to compare the total amount of energy required to break these bonds to the total amount of energy released when these bonds form, these HCl bonds form, which is where this topic comes in, energy in, energy out, in which we measure bond energy, right? Now, what I did above was I provided a theoretical value, for example, 431 energy that was required to break this bond. Now, in the exam, you are going to be given a table in which there will be written some bond energies of some molecules in the form of this table, right? For example, I know this is given to me in the exam. You do not need to remember this at all, but I know that hydrogen bond is 436, Cl bond is 242 kilojoules per mole, and HCl bond is 431 kilojoules per mole. These are the energies that I need to use in order to find out if the overall reaction is endothermic or if it is exothermic. And I will do so by measuring the enthalpy. Now, the formula for enthalpy change for when these types of bond energies are involved is the energy of the reactants minus the energy of the products, right? So let's say if I want to calculate the enthalpy change for this particular reaction, which is H2 plus Cl2 will give me 2 HCl. As you can see that the bonds are already made for these two reactions, and let me make a bond for this as well. Right, now that that's completed, we can now calculate the enthalpy change. Now, these energies will be provided to me in the exam paper, right? So I can now just plug in the values. For example, 436 can go for hydrogen, 242 will go for Cl2, and 431 times 2 will go for HCl. So let's plug in these values and see for ourselves what are we getting. So 436 plus 242 will give me 2 times 431. Okay, so what's the answer coming? So 678 minus 862, because there's an equal sign in between, and the products should be minus from the reactants, right? We learned from above in the above formula. So if I minus this as well, I will be getting minus 184 kilojoules per mole. Okay. Now, this particular negative value will indicate to me that the above reaction, the overall above reaction is an exothermic reaction, because the enthalpy change is coming as a negative value, right? So what this basically means, the chemicals are losing 184 kilojoules of moles of energy to their surroundings, making it an exothermic process. Now, although you don't have to, but it is always easier to draw out all of the molecules using their displayed formula like we did for the above reaction, so you have a better idea as to how many bonds are actually present. It's better if you do it because it's better for practice as well and for a better idea in your calculations. Now, moving on to the second example, we have nitrogen plus 3 hydrogen bonds, and which will give us 2 molecules of ammonia. So I have a nitrogen bond over here. I can see that 941 kilojoules of moles for nitrogen, 436 kilojoules of moles for hydrogen, and 391 kilojoules of moles for 1 molecule of ammonia. So if I draw the displayed formula for this whole reaction, I will be getting something like this. So 3 molecules of 1 molecule of nitrogen plus 3 molecules of hydrogen, like so, which will give me 2 molecules of ammonia, right? Right, now that's done. So what do I know about this? I know that I will be needing to break this nitrogen-nitrogen bond and all these individual hydrogen-hydrogen bonds, which will react to form 2 molecules of ammonia. So let's label them. These are breaking bonds and these are the forming bonds. So now if you recall enthalpy change, which was energy of the reactants minus energy of the products, we can just plug in our values and find out the overall enthalpy change. So I have one molecule of nitrogen, which will give me an energy of 1 times 941. Actually, it is written over here in the table above. And I have 3 molecules of hydrogen. And this is the energy given to me for one singular bond. I have 3 of them, right? So I will need to multiply 436 times 3 in order to input the correct amount of energy required to break all 3 of these hydrogen-hydrogen bonds. So let's input them right here. So 1 times 941 plus 3 times 436, which will give me, let's move on to the products. I will have to look at the table again and see that there is only one NH bond energy that is given to me. If I count the NH bonds individually, see, that's why I told you to draw the displayed formula, as it gives you the correct idea and the correct proportion of what is forming and what is breaking. So one NH bond is 391 kilojoules of energy. I have 6 of them. 1, 2, 3, 4, 5, 6. Clear? So I will need to multiply 391 times 6 in order to get the correct energy required to break the ammonia, to form the ammonia molecules. Okay, so let's work this out. I will be getting 2249 minus 2346. If this comes to this side, it will be a minus sign, and the equation that we had was energy of the reactants minus the energy of the products. So this is going to be give me an answer of minus 97 kilojoules per mole, and this is the enthalpy change. Now, because my enthalpy change is coming as a negative value, this will indicate to me that this above reaction is an exothermic reaction, thus making it a negative enthalpy change, which I'm getting. So this wraps up our chemical energetics part 3 and the chemical energetics topic for the IGCSE syllabus. If you have any questions regarding this video, I will recommend you to drop a comment down below in the comment section, and I will respond to each and every comment that gets posted. Thank you so much for watching, and I will see you in the next video.